Reality is not what it appears to be. The very fabric of space is a seething foam of energy at the smallest scales, while it forms a cosmic web of galaxies at the largest. This is not science fiction, but the frontier of our understanding. By the end of this journey, you will see the universe as a deeply interconnected whole, from its quantum foundations to its grandest structures. We will explore how empty space is not empty at all, and how the dance of particles builds everything we know. How can something so chaotic at its heart create the stable world we experience? A majestic cathedral does not reveal its hidden foundations, the intricate lattice of stone and steel that allows its spires to touch the sky. In the same way, the visible universe, with its swirling galaxies and shining stars, rests upon a deep and hidden architecture. This is the deep structure of reality, the fundamental framework of everything that exists. It is not one single thing, but a cascade of layers, from the unimaginably small to the cosmically vast, each with its own distinct rules and behaviors. What we casually call empty space is the first and greatest illusion. It is not a void, but a complex, dynamic entity, a stage that is itself an active participant in the cosmic drama. This single idea shatters the classical view of a passive, absolute space, and completely contradicts our everyday intuition. The ancient philosopher Plato hinted at this, proposing that the world of our senses is merely a shadow cast by a deeper, more perfect realm of forms. Today, physicists like Carlo Rovelli extend this thought, suggesting that even properties like space and time are not fundamental, but emerge from a web of relationships between events. So if reality is built in layers, what could possibly form the base, the absolute bedrock of existence? The search for that answer pulls us down, past atoms, past nuclei, to the very edge of meaning itself. This turbulent foundation of reality operates at a scale so small it defies imagination, the Planck scale. Here, the smooth fabric of spacetime we take for granted dissolves into a seething, chaotic froth known as the quantum foam. This is not a physical substance you could touch, but a theoretical concept born from the violent marriage of quantum mechanics and general relativity. Picture the most violent ocean storm you can conceive, where the very surface of the water is not a flat plane but a churning, chaotic mess of peaks and troughs. Now imagine that the ocean itself is the fabric of space and time. At this unimaginably tiny scale, spacetime is not smooth. It is a turbulent sea of fluctuating geometry, where bubbles of distorted space constantly form and pop into existence. This roiling activity is so intense that the very ideas of a definitive here and a definitive there, or a clear before and after, begin to lose all meaning. It was the visionary physicist John Wheeler who first gave this chaotic foundation a name. He envisioned a reality where the smooth stage of Einstein's universe, at its very foundation, is actually rough and foamy. In this realm, the energy of empty space is in constant, violent flux. These quantum fluctuations are so powerful that they can momentarily conjure pairs of virtual particles into existence. Particles and their antimatter counterparts that borrow energy from the vacuum only to annihilate each other and vanish an instant later. This endless dance of creation and destruction is the very bedrock of reality. From this frenetic activity, the possibility of even stranger structures emerges. Tiny, spontaneous wormholes, minuscule tunnels through the fabric of space-time, could blink in and out of existence, connecting distant points for a fleeting moment before the foam swallows them again. So if this is the true nature of our foundation, a reality built upon a chaotic, bubbling sea, what does that say about the world we perceive? Is our smooth, continuous experience of reality just a grand illusion, a stable average of infinite, frantic vibrations? Understanding this chaotic origin is the first step to unraveling the greatest mystery of all. How from such utter turmoil the stable particles that build our world ever manage to emerge. This ceaseless churn of the quantum foam is not empty theater. It has a cast of characters, actors that flash into existence for the briefest of moments before vanishing back into the void. These are virtual particles, the ephemeral stuff of reality. The vacuum of space itself is a vibrant, energetic arena, far from the true nothingness we might imagine. This startling fact was confirmed by a clever experiment known as the Casimir effect. If you place two perfectly smooth, uncharged metal plates extremely close together in a vacuum, they are gently pushed toward each other by an invisible force. What is pushing them? The answer lies in the space between them. Outside the plates, a whole spectrum of virtual particles can flicker into being. But in the narrow gap between them, only particles with specific wavelengths can appear. This imbalance in the quantum activity outside versus inside creates a subtle pressure that nudges the plates together. Empty space is actively pushing on them. These ghostly particles operate under a strange cosmic rule, the Heisenberg uncertainty principle. This principle allows for a temporary loan of energy, a brief withdrawal from the universe's bank that must be paid back almost instantly. A particle and its antiparticle twin can spontaneously pop into existence, live for a fleeting moment, and then annihilate each other, returning the borrowed energy. They are the primary actors on the stage of the quantum foam, and their role is absolutely critical. They are not merely mathematical ghosts. These fleeting fluctuations are the very mechanism by which forces like electromagnetism are transmitted. A stable electron, for instance, is constantly surrounded by a cloud of these virtual particles, and their presence subtly alters the electron's properties. This effect is precisely measured in the Lamb shift, a tiny but crucial change in the energy levels of hydrogen atoms that could only be explained by this frantic, invisible activity. To visualize this, think of a pot of water simmering on a stove. The surface of the water is never perfectly still. Bubbles of steam constantly form, rise, and pop. Each bubble is like a virtual particle pair, a temporary disturbance in the underlying field. Most vanish without a trace, but their collective activity defines the very nature of the simmering water. The great physicist Richard Feynman, a master of explaining the quantum world, once noted that the strange behavior of these particles is not something we can just explain away. It is the way nature works. We must accept it as a fundamental characteristic of our reality. So if this entire foundation is built upon such fleeting, temporary events, a constant dance of apparitions, how does anything permanent ever come to be? How does this ephemeral chaos give rise to the stable, enduring particles that eventually form planets, oceans, and us? So how does this chaotic dance of apparitions ever produce something solid and lasting? The answer is a matter of energy. For a virtual particle to step out of the wings and become a real, permanent actor on the cosmic stage, it needs a significant infusion of energy. This is the moment of creation, the transition from fleeting possibility to stable matter. In the intense heat of the early universe, or within the colossal collisions of modern particle accelerators, that energy is provided, locking these particles into a lasting existence. This entire cast of fundamental characters is catalogued in a triumph of human understanding known as the Standard Model of Particle Physics. Think of it as a periodic table for the absolute building blocks of reality. On one side, you have the matter particles. These are the quarks, which combine to form protons and neutrons, and the leptons, which include the familiar electron. On the other side are the force carriers, the particles that mediate the fundamental interactions. The photon carries the electromagnetic force, while the gluon glues quarks together inside atomic nuclei. But there was a missing piece to this puzzle for a very long time. Why do some of these particles have mass, while others, like the photon, are massless? The answer emerged from a theory proposing an invisible field that permeates all of space, the Higgs field. As fundamental particles move through this field, they interact with it. Some particles, like quarks and electrons, plow through this field as if moving through an invisible molasses, and this resistance is what we experience as mass. The discovery of the Higgs boson at the Large Hadron Collider was a monumental event. This particle is not the field itself, but a tiny, localized excitation in the Higgs field, a ripple that confirmed the field's existence. This leads to a profound shift in perspective. Every electron in the universe is not a tiny, solitary ball. It is a localized knot of energy, an excitation, in a universal electron field that stretches across all of spacetime. The same is true for every quark and every force carrier. They are all tiny vibrations in their own unique, omnipresent fields. The solid table in front of you, the air you breathe, your own body, are all, at their most fundamental level, nothing more than complex patterns of excitation in these invisible, interwoven fields. So what does this say about the solidity of the world you feel? It suggests that the chair you are sitting on is not a solid object in the classical sense, but a dense, stable vibration in the cosmic field, a standing wave of immense complexity. With these stable particles now in place, the universe had the bricks and mortar it needed to build something far grander, the atoms that would eventually weave the tapestry of the cosmos. These stable particles are the universe's ultimate artisans, assembling themselves into the very elements that write the story of chemistry. Every single substance you have ever touched, from the water in a glass to the screen you are looking at now, is a testament to this atomic architecture. The nucleus, a tight cluster of protons and neutrons, forms the atom's dense, heavy heart. Orbiting this core is a cloud of electrons, so light and fast they defy any attempt to pin them down. The entire identity of an element, what makes gold gold and oxygen oxygen, is determined by just one number, the count of protons in its nucleus. This simple integer dictates its place on the periodic table, that majestic map of all possible chemical substances. Yet, the atom itself is a realm of profound strangeness. The classic image of electrons whizzing around the nucleus like planets around a sun is deeply misleading. In the quantum world, electrons do not follow neat, predictable paths. They exist as smeared-out probabilities, inhabiting fuzzy regions called orbitals. These are not orbits, but three-dimensional shapes, clouds of potential where an electron is most likely to be found. It is as if the planet Earth were not a solid ball, but a diffuse, shimmering haze that occupies its entire orbital path at once. This quantum behavior is the true engine of chemistry. The interactions between these electron clouds, the ways they attract and repel and share space, govern how atoms link together to form molecules. It is this delicate quantum dance that creates the staggering diversity of our world, from the hardness of diamond to the flexibility of rubber, from the inert stability of argon gas to the explosive reactivity of sodium. We are literally made from this stardust. As the astronomer Carl Sagan so poetically reminded us, the nitrogen in our DNA, the calcium in our teeth, the iron in our blood, were all forged in the interiors of collapsing stars. We are a way for the cosmos to know itself, but this revelation presents an immediate and puzzling contradiction. If an atom is mostly empty space, with a tiny nucleus and a vast, fuzzy electron cloud, why does matter feel so solid? Why does your hand not simply pass through the table when you press on it? The answer lies not in the atoms themselves, but in the powerful forces that emerge when their diffuse electron clouds meet, a phenomenon that paves the way for the next great level of cosmic structure. That profound sense of solidity you feel when your hand presses on a table is a magnificent illusion, born from the invisible architecture of molecules. Individual atoms, those mostly empty quantum systems, are the universe's Lego bricks, but their true power is unlocked only when they connect, forming molecules that become the next, more complex layer of reality's deep structure. The forces that bind them are chemical bonds, the fundamental rules of cosmic construction. These bonds come in several types, each with its own character. An ionic bond is like a dramatic transfer of allegiance, where one atom donates an electron to another, creating oppositely charged ions that cling together in a powerful embrace, as seen in common table salt. A covalent bond is more like a partnership, a firm handshake where two atoms agree to share one or more of their outermost electrons, creating a stable, mutual arrangement. This is how the oxygen we breathe, with its two atoms, is held together. In a metal, atoms pool their outer electrons into a communal sea, which is why metals are such good conductors of both electricity and heat. The specific shape and structure of a molecule, dictated by these quantum handshakes, determine its properties entirely. A simple molecule like water, with its two hydrogen atoms clinging to one oxygen at a specific angle, has unique properties like surface tension and the ability to dissolve so many substances, making it the solvent of life. At the other extreme, the DNA double helix is a masterpiece of molecular architecture, a twisted ladder of precisely bonded atoms that encodes the entire blueprint for a living organism. Understanding these bonds required a quantum leap in thinking. The pioneering chemist Linus Pauling realized that the chemical bond was not a simple mechanical link, but a quantum phenomenon. He showed that atoms bond in ways that minimize their energy, creating the most stable arrangements possible. A classic example is the hydrogen molecule. Two separate hydrogen atoms will spontaneously come together and form a covalent bond because the resulting molecule is more stable, at a lower energy state, than the two atoms were apart. It is a union dictated by the probabilistic laws of the quantum world. How is it that these simple rules of attraction and sharing, governed by the fuzzy clouds of electron probability, can give rise to the staggering complexity of a single cell, let alone a conscious mind? The answer lies in aggregation. As these molecules accumulate, they begin to build the solid matter of our everyday world, the very materials that define our physical experience. The simple act of water freezing into ice reveals a profound truth about reality. As the temperature drops, individual water molecules, each a tiny V-shaped structure, begin to slow their frantic dance. They no longer slide past one another freely. Instead, they lock into a precise, repeating arrangement, a rigid lattice that extends in every direction. This is the birth of a solid from a liquid, a phase transition where countless individual components suddenly act as one collective entity. This emergence of collective behavior from simple rules is the domain of condensed matter physics, the science of how atoms and molecules organize themselves into the solids and liquids that make up our tangible world. The key to this organization is often a crystal lattice, a perfectly periodic, three-dimensional pattern that repeats like an endless wallpaper design. In a diamond, carbon atoms form an incredibly strong tetrahedral lattice. In a grain of salt, sodium and chlorine ions alternate in a simple cubic grid. This underlying architecture dictates the material's very essence. But how does this architecture translate into properties we can use? The answer lies in a concept called band theory. Inside a solid, the energy levels available to electrons are not the discrete rungs of a single atom's ladder. They smear out into broad bands, like wide highways instead of narrow paths. A crucial gap, the band gap, exists between these highways. Whether a material is a conductor, an insulator, or a semiconductor depends entirely on how these bands are filled with electrons and the size of this gap. In a metal, the highest band is only partially full, allowing electrons to flow freely when a voltage is applied, like cars on an open freeway. In an insulator, the bands are completely full, and the gap to the next empty band is so large that electrons cannot jump across. It is a traffic jam with no exit. This is why copper wire conducts electricity, while the rubber coating around it does not. These collective behaviors give rise to truly astonishing emergent phenomena, properties that simply do not exist in the individual atoms. Superconductivity occurs when electrons in a material pair up and move in perfect, frictionless coordination, allowing electrical current to flow forever without any loss. Magnetism is another emergent dance, where the intrinsic spins of billions of electrons align to create a persistent magnetic field. To visualize this, think of a vast crowd of people in a stadium. Each person is an individual capable of independent movement. But when they participate in a wave, a new entity is born, a rolling pattern that moves around the arena. No single person is the wave exists only as a collective behavior of the crowd. This is the heart of physicist Philip Anderson's famous assertion, "More is different." New laws and new phenomena emerge at every level of complexity that cannot be, not even in principle, be reduced to the laws of a simpler level. So why is glass transparent while wood is opaque? The answer is not in a single silicon or carbon atom, but in the specific arrangement of their energy bands, which either permit or block the passage of light. This understanding of bulk matter, of how quantum rules scale up to create the materials of our world, is the final preparation for the universe's most ambitious construction project, the assembly of planets, stars, and the great cosmic web itself. From the swirling dance of molecules and the emergent laws of solids, a new cosmic architecture begins to take shape. The same forces that give glass its transparency and metal its strength now operate on an infinitely grander scale, gathering scattered stardust into entire worlds. This is the birth of a solar system, a process we can witness today in the glowing nurseries of nebulae like Orion. There, vast clouds of gas and dust, the remnants of long-dead stars, begin to collapse under their own immense gravity. As this cloud contracts, a fundamental principle of physics takes over: conservation of angular momentum. Just as a figure skater spins faster as they pull their arms in, the cloud spins more and more rapidly as it shrinks. This spinning motion flattens the cloud into a giant, whirling disk, with the vast majority of the material falling into the center to ignite as a new star. The remaining material in the disk, a thin soup of gas and dust, is the raw stuff of planets. Think of a chef spinning a ball of pizza dough. As it spins, it flattens into a disk, and tiny bits of dough can be thrown from the edges. In the protoplanetary disk, these bits are not dough, but microscopic dust grains. They begin to stick together through static electricity and gentle collisions, a process called accretion. These tiny clumps, known as planetesimals, are the building blocks of planets. They sweep through the disk, gathering more and more material through their own gravitational pull, growing from pebble-sized rocks to mountain-sized bodies, and eventually to worlds. The final architecture of the solar system is a direct result of the intense heat from the young star. Close to the stellar furnace, only materials with high melting points, like metals and rocks, could remain solid. This is why the inner planets like Earth and Mars are dense and rocky. Farther out, beyond the frost line, temperatures were low enough for volatile compounds like water, ammonia, and methane to freeze into solid ice. These ices, combined with abundant hydrogen and helium gas, allowed the outer planets to grow to immense sizes, becoming the gas and ice giants like Jupiter and Neptune. This entire cosmic construction project is governed by a delicate interplay of forces. Gravity is the primary architect, pulling everything together. But electromagnetic forces are the master craftsmen, determining the chemical bonds that define a world's composition, whether it will be a scorching ball of iron and silicon or a frigid globe of swirling hydrogen. Our understanding of this process has been revolutionized by missions like the Kepler Space Telescope, which has revealed thousands of exoplanets orbiting distant stars. We now know that solar systems are common, but each one is a unique experiment in planetary formation. This discovery forces us to ask a deeply reflective question. With so many worlds in the galaxy, what specific conditions are necessary for a planet to cross the threshold from a barren rock to a living world? The aggregation of these countless solar systems, each one a gravitational island, is the next critical step in building the largest structure in the universe. Our Sun is a sphere of incandescent plasma, a continuous thermonuclear explosion held together by its own gravity. Every second, deep within its core, 600 million tons of hydrogen fuse into helium, releasing the staggering torrents of energy that have nourished life on our world for billions of years. This is the life of a star, a cosmic engine whose entire existence is a delicate and protracted battle between two titanic forces. Gravity relentlessly tries to crush the star into a tiny point, while the outward pressure from nuclear fusion pushes back, creating a stable, dynamic equilibrium. The mass of a star at its birth is its destiny, a single number that dictates its entire life story, from its brilliant prime to its spectacular death. A star like our Sun will spend 10 billion years fusing hydrogen in its core. When that hydrogen fuel is finally exhausted, the core contracts and heats up, allowing the star to begin fusing helium into carbon and oxygen. This new furnace causes the star's outer layers to expand dramatically, transforming it into a red giant, a swollen beacon that will one day engulf the inner planets. For more massive stars, the journey is far more violent. Their immense gravity allows them to achieve higher core temperatures, enabling them to forge progressively heavier elements, building a layered structure like an onion, with shells of silicon, neon, and oxygen, all surrounding an inner core that is steadily turning to iron. This is the end of the line for stellar fusion. Fusing iron does not release energy, it consumes it. With its energy source cut off, the star's core collapses catastrophically in less than a second, leading to a supernova explosion of almost unimaginable power. In that single, brilliant flash, the star outshines its entire galaxy, and in the ferocious inferno, elements heavier than iron are forged, from the gold in a wedding ring to the uranium in the Earth's crust. The pioneering astrophysicist Arthur Eddington once pondered this stellar alchemy, asking where a star could find the power to sustain its heat for so long. His answer pointed to a subatomic source, the conversion of mass into pure energy. This process seeds the cosmos with the raw materials for everything. A supernova is both an end and a beginning, a violent dissolution that scatters the elements of life across interstellar space. These newly forged atoms, blown into the void by stellar winds and colossal explosions, become the ingredients for new stars, new planets, and eventually, new life. How does the death of one star contribute to the birth of another? The enriched gas clouds, now heavy with carbon, oxygen, and iron, collapse under gravity to form a new generation of stars, planets rich in minerals and the potential for biology. We are the legacy of these long-vanished giants. These vast cities of stars, these galaxies, are the fundamental building blocks of the visible cosmos. Our own Milky Way is a majestic spiral, a swirling disk containing hundreds of billions of individual suns, each with its own potential for planets and life. This is not a random scattering of lights. It is a gravitationally bound island, a single, coherent structure on a scale that dwarfs human comprehension. Edwin Hubble, peering through the Great Telescope at Mount Wilson, was the first to properly classify these distant nebulae as independent galaxies far beyond our own. He sorted them into a cosmic zoo, primarily spirals like our own, the smooth football-shaped ellipticals, and the chaotic, misshapen irregulars. At the heart of most of these stellar metropolises, including our own, lies a mysterious and terrifying engine, a supermassive black hole. These are not the destructive monsters we often imagine, but rather gravitational anchors, whose immense presence helps shape the entire galaxy. To understand the dynamics of a spiral galaxy, picture a whirlpool in a river. The stars and gas do not orbit at a single, uniform speed. Just as the water in a whirlpool moves faster near the center, you might expect stars closer to the galactic core to race around much more quickly than those on the outskirts. But observations reveal something astonishing and deeply puzzling. The orbital speed of stars remains almost constant, regardless of their distance from the center. This is like the outer edges of the whirlpool spinning just as fast as the violent center, a phenomenon that defies the laws of gravity as we understand them with visible matter alone. The only plausible explanation is that the entire galaxy is embedded within a vast, invisible halo of something we cannot see, dark matter. This mysterious substance provides the extra gravitational glue that binds these fast-moving outer stars to the galaxy, preventing them from flying off into the void. So what governs the life and evolution of these colossal star cities? They are not static. Galaxies collide and merge in a slow cosmic dance, their gravitational interactions distorting their beautiful spiral arms and triggering bursts of new star formation. Our own Milky Way is on a collision course with the Andromeda Galaxy, a monumental event that will unfold over billions of years. This grand interplay raises a profound question. If galaxies are the building blocks, how are they themselves arranged within the cosmos? Do they float in isolation, or are they part of a structure even more immense, a true architecture of the universe? The outer stars of a spiral galaxy should be drifting lazily in their orbits, slowed by the weakening grip of gravity. Yet they race, held fast by an unseen hand. This was the startling discovery of astronomer Vera Rubin, who meticulously mapped the rotation of galaxies and found a profound discrepancy. The stars at the edges were moving just as quickly as those near the brilliant core, a cosmic traffic violation that defied the laws of motion. The only logical explanation was that a vast, invisible mass was holding everything together, a ghostly gravitational glue she called dark matter. This mysterious substance does not emit, absorb, or reflect any light. It is completely invisible to our telescopes, yet its gravitational pull is the dominant force sculpting the largest structures in the universe. You can think of it like the wind. You cannot see the air itself, but you can clearly see its effects as it bends the branches of trees and drives clouds across the sky. In the same way, we cannot see dark matter, but we observe its profound influence on the motion of galaxies and the very path of light itself. Its role in the cosmic story is absolutely fundamental. In the early universe, the slight gravitational tugs from dark matter provided the initial seeds, the gathering points for ordinary matter to clump together. Without this invisible scaffolding, the primordial gas would have been too evenly distributed, and the gravitational wells necessary for the first stars and galaxies to form would never have deepened. Dark matter drew the blueprint for the cosmic web long before the first star ever shone. So what could this invisible substance possibly be? The leading candidates are exotic particles that barely interact with the normal matter we are made of. One prominent theory points to WIMP, or weakly interacting massive particles. These hypothetical entities would have mass, allowing them to exert gravity, but they would pass through our world like ghosts, rarely, if ever, colliding with the atoms of your body. For decades, physicists have been hunting for these elusive particles in exquisitely sensitive experiments located deep underground, shielded from cosmic rays. They wait patiently for the telltale, minuscule bump that would signal a dark matter particle interacting with their detector. Vera Rubin herself reflected on the evidence, stating that we have been forced to infer the presence of dark matter from its gravitational effects, a conclusion that is inescapable. This leads to a deeply puzzling question. If dark matter is everywhere, forming a vast ocean through which our entire solar system swims, why does it remain so stubbornly hidden from our direct view? Its pervasive yet ghostly nature is the key to understanding how the cosmic web, the final layer of reality's architecture, could ever have taken shape. The ghostly pull of dark matter built the cosmic web, but a far stranger force now governs its ultimate fate. In the late 1990s, two independent teams of astronomers made a discovery so shocking it overturned a fundamental assumption about the cosmos. By carefully observing distant supernova, the cosmic mile markers, they found that the universe is not expanding at a steady pace, nor is it slowing down as everyone expected. It is accelerating. The fabric of space itself is stretching apart at a faster and faster rate, driven by a mysterious repulsive force we call dark energy. This was the equivalent of tossing a ball into the air and watching it not only fail to fall back down, but shoot away from you into the sky with ever-increasing speed. To explain this bizarre behavior, scientists turned to an old idea from Einstein himself, the cosmological constant. This represents a constant energy density inherent to the vacuum of space itself. As the universe expands and more space comes into existence, more of this repulsive energy appears, driving the expansion ever faster. Think of it like a spring, but one that pushes outward instead of pulling inward. With every stretch, its pushing force grows stronger. This dark energy is not a minor component. Measurements from satellites like Planck reveal it makes up a staggering 68% of the total energy budget of the universe. Dark matter accounts for about 27%, and all the normal matter we see, every star, planet, and galaxy, constitutes a mere 5%. We are living in a universe dominated by an invisible, repulsive force we do not understand. This has profound consequences for the large-scale structure of reality. Dark energy acts as a kind of cosmic opposition to gravity's relentless pull. On the scale of galaxy clusters, gravity still wins, holding these massive structures together. But on the vast intergalactic scale, dark energy is the dominant player, pushing galaxies apart from one another and determining the future evolution of the cosmic web. Some theories suggest dark energy might not be a simple constant, but a dynamic field that changes over time, known as quintessence. This would mean the strength of this repulsive force could evolve, leading to different possible futures for the cosmos, from a gradual thinning of all structure to a catastrophic rip that tears apart the very fabric of spacetime. So is dark energy a fundamental property of empty space, a fixed feature of the vacuum, or is it something more exotic, a fifth force of nature that we have only just begun to detect? Unraveling this mystery is the final step in mapping the deep structure of reality, from the quantum foam to the accelerating cosmic web. This faint glow is a fossil of creation itself, the cosmic microwave background radiation. It is the oldest light in the universe, a snapshot from a time when the cosmos was a mere 380,000 years old. This discovery was one of the great accidents of science. Two radio astronomers, Arno Penzias and Robert Wilson, were troubleshooting a persistent, mysterious hiss in their giant horn antenna. They scrubbed away pigeon droppings and checked every connection, but the faint, uniform noise remained, coming from every direction in the sky. They had stumbled upon the cooled remnant of the Big Bang's primordial fireball. When the universe was in its infancy, it was an opaque, searing hot plasma, so dense that light was trapped, constantly scattering off a soup of particles. Then, as the cosmos expanded and cooled, a monumental event occurred: recombination. Electrons were finally captured by protons, forming the first stable hydrogen atoms. With the charged particles now bound into neutral atoms, the fog cleared. Photons, which had been trapped for eons, were suddenly set free on a journey across the universe. The light that began its voyage that day is what we now detect as the CMB, a cold whisper after 13.8 billion years of travel, cooled by the expansion of space to just a few degrees above absolute zero. Yet, this background is not perfectly smooth. When we map its temperature with incredible precision, using satellites like COBE and Planck, we see a mottled tapestry of tiny variations. These minute fluctuations, mere millionths of a degree, are the most important fossils we will ever find. They are the gravitational seeds from which everything grew. Slightly denser regions, imprinted as slightly cooler spots in the CMB, held just a little more gravitational pull. Over billions of years, they drew in more and more dark matter and gas, eventually becoming the great clusters and superclusters of galaxies we see today. The emptier regions became the vast cosmic voids. The entire architecture of the cosmic web is written in this ancient code. How could these minute ripples, spread across the entire sky, have such a coherent, large-scale pattern? The leading theory points to a breathtaking event in the universe's first fraction of a second, a period of hyper-expansion called inflation. This theory proposes that the universe underwent an exponential growth spurt, magnifying quantum fluctuations from the quantum foam itself into the macroscopic density variations that seeded the cosmos. It is as if a single, microscopic wrinkle on a tiny balloon was suddenly stretched to continental proportions when the balloon was inflated to the size of the Earth. Nobel laureate George Smoot, upon seeing the first detailed map of these fluctuations from the COBE satellite, famously remarked that it was like seeing the face of God. These primordial whispers are our most direct link to the universe's absolute beginning. They tell us of its initial conditions, its composition, and its ultimate fate. What other secrets are encoded in this faint, cosmic afterglow? And what does the specific pattern of these seeds reveal about the mysterious forces of dark matter and dark energy that would go on to sculpt them? Those faint temperature ripples in the cosmic microwave background were the universe's opening chord. For the first few 100 million years, the cosmos remained a dark, featureless expanse of hydrogen and helium gas, still echoing with the faint afterglow of creation. But within that smoothness, the tiny density variations imprinted by inflation were waiting. Slightly denser regions, even those with just a few more particles in a volume the size of a galaxy, held a tiny bit more gravitational pull. Over cosmic time, this small advantage became everything. Gravity is an amplifier. A region with a little more mass pulls in a little more gas from its surroundings. With more mass, its gravitational pull grows stronger, allowing it to attract even more matter in a runaway process of cosmic growth. This is gravitational instability, the engine that built the universe from a near-uniform haze into the grand structure we see today. But the primary material for this construction was not the ordinary atoms we are made of. It was the invisible, mysterious dark matter. Because dark matter does not interact with light or normal matter through any force except gravity, it was free to begin collapsing first, long before the first stars could form. It fell into the gravitational wells of those initial ripples, building a vast, invisible scaffolding across the cosmos. The ordinary matter, the gas that would eventually form stars and galaxies, simply followed this dark matter skeleton, flowing along its gravitational contours. We can watch this entire process unfold inside a supercomputer. Cosmologists run simulations that start with a universe almost perfectly smooth, seeded with those same tiny fluctuations we see in the cosmic microwave background. They set the rules, inputting the known amounts of dark matter and dark energy, and then let gravity do its work over billions of simulated years. The result is always the same, a cosmic web. It is a vast, interconnected network of dark matter filaments, stretching across the emptiness like the threads of a spider's web. Where these filaments intersect, massive knots form, the future homes of giant galaxy clusters. Between the threads are the immense cosmic voids, vast deserts of space nearly empty of galaxies, spanning hundreds of millions of light years. This is not a static sculpture. It is a dynamic, flowing river of matter. Galaxies are not scattered randomly. They trace the web's architecture, lining up along the dark matter filaments like pearls on a string, and crowding into the dense clusters at the intersections. The Sloan Digital Sky Survey has given us our most detailed map of this local cosmic geography. By meticulously charting the positions and distances of millions of galaxies, it has revealed the web in stunning detail, showing the Great Wall of Galaxies and the vast emptiness of the Boots Void. How does a force of pure attraction, gravity, create such an intricate, web-like pattern instead of just one giant clump? The answer lies in the initial conditions. Those primordial ripples were not isolated dots. They were connected in a network of crests and troughs. Gravity simply exaggerated this pre-existing connected pattern, pulling matter into the ridges and draining it from the valleys. The largest things in the universe are not the clusters or the voids, but the filaments themselves, delicate threads of gravity that weave the entire observable cosmos into a single, coherent structure. This magnificent web is the final layer in our journey, the ultimate expression of the deep structure of reality. This vast cosmic skeleton stretches across the emptiness, a delicate filigree of gravity and shadow on the largest scales we can observe. The cosmic web is the final, grandest layer of reality's architecture. A network of galaxy clusters, thread-like filaments, and immense, echoing voids that spans billions of light years. We are not merely looking at a collection of isolated galaxies. We are seeing the structure of the universe itself. At the nodes of this web, where the threads intersect, lie the dense galaxy clusters. These are the metropolises of the cosmos, where thousands of galaxies swarm together in a relatively small volume of space, bound by their mutual gravitational pull. Stretching between these clusters are the filaments, long, delicate bridges of dark matter and gas, along which galaxies are strung like pearls on an invisible string. And between these threads lie the voids, the cosmic deserts. These are regions of staggering emptiness, so vast that a single void can be hundreds of millions of light years across, containing only a few isolated galaxies. This entire structure acts as a cosmic highway, guiding the flow of matter and influencing the life story of every galaxy within it. A galaxy living in a dense cluster has a very different existence from one in a lonely filament. In the cluster, galaxies are constantly interacting, sometimes colliding and merging, their gas stripped away by the hot intracluster medium, which can shut down star formation. A galaxy in a filament, however, may enjoy a more peaceful existence, with a steady flow of fresh gas from the web allowing it to form new stars for much longer. The astrophysicist J. Richard Gott perfectly captured this structure when he compared the universe to a sponge, an intricate arrangement of dense matter and empty space. This analogy is powerful because it conveys the connected nature of the cosmos, the way the web is a single, continuous entity. An even more striking comparison can be made to the neural network in a brain. The dense galaxy clusters act like the neurons, the processing centers, while the long, thin filaments resemble the axons, the connections that carry signals and allow the entire network to function as a coherent system. But this grand design is not static. Dark energy, that mysterious repulsive force, is the great sculptor of the web's long-term future. As the universe's expansion accelerates, the threads of the cosmic web are being stretched. The distance between clusters grows, and the flow of fresh gas along the filaments that feeds galaxy growth is gradually slowing down, like a river turning to a trickle. This leads to a profound question about the permanence of this magnificent structure. Is the cosmic web a fixed feature of our universe, or will the relentless push of dark energy eventually tear this cosmic skeleton apart, isolating all galactic islands in an ever-cooling sea of emptiness? To answer that, we must look deeper into the forces that bind this web together. The same forces that have guided our entire journey from the quantum foam. A galaxy cluster is one of the most massive structures in the universe, and its gravity warps the very space around it so profoundly that it bends the path of light itself. This is gravitational lensing, a cosmic phenomenon predicted by Einstein's theory of general relativity. It works on a simple but profound principle. Mass tells spacetime how to curve, and curved spacetime tells light how to move. A massive object like a galaxy cluster acts as a lens in space, distorting and magnifying the light from galaxies that lie far behind it. This gives us a natural, cosmic telescope of immense power. We can see two primary effects. In strong gravitational lensing, the alignment is so perfect that we see multiple, sharply defined images of the same background galaxy, or beautiful, stretched arcs of light encircling the foreground cluster like a halo. These Einstein rings and arcs are the universe's most dramatic demonstration of warped space. More common and more subtle is weak gravitational lensing. Here, the foreground mass is not concentrated enough to create multiple images, but its gravity still imposes a faint, coherent distortion on the shapes of thousands of distant background galaxies. It is as if you are looking at a field of stars through the rippled glass of an old window pane, where every pinpoint of light is slightly stretched and sheared in a specific direction. This subtle shearing is the key to mapping the invisible. The vast halos of dark matter that envelop galaxy clusters and form the cosmic web do not emit light, but they do exert gravity. By meticulously measuring the tiny, systematic distortions in the shapes of millions of galaxies, astronomers can trace out the distribution of this unseen mass. It is like detenting the shape of a hidden object buried under a rug by carefully studying the slopes and contours of the fabric covering it. Projects like the Hubble Space Telescope's frontier fields have used this technique to peer deeper into the universe than ever before. By staring at massive galaxy clusters acting as natural lenses, Hubble has revealed incredibly faint, magnified galaxies from the very dawn of cosmic time, objects that would otherwise be forever beyond our view. This bending of light creates a direct bridge between the largest scales and the smallest. The same fundamental physics that governs the path of a photon around a galaxy cluster also applies to the quantum foam, where the fabric of spacetime is itself a turbulent sea. How can the simple act of watching light bend allow us to weigh the invisible skeleton of the cosmos and glimpse the first flickers of galactic dawn? Gravitational lensing reveals the cosmic web's grand design, but it also points to a glaring rift at the very heart of physics. Einstein's theory of general relativity paints a beautiful picture of gravity as the smooth, geometric curvature of spacetime, perfectly explaining the dance of planets and the bending of light around galaxies. Yet, this elegant picture completely shatters when we try to apply it to the frenetic, probabilistic world of the quantum foam. At the Planck scale, where spacetime itself becomes a seething, foamy chaos, the rules of general relativity simply break down. This is the greatest unsolved problem in fundamental physics, the quest for a theory of quantum gravity. For all the other forces of nature, we have a quantum description. The electromagnetic force is carried by photons, the strong nuclear force by gluons, all behaving as discrete packets of energy, but gravity stands alone, stubbornly classical. We have no quantum particle for gravity that fits neatly into the standard model. This means we have no way of describing what gravity is doing in the universe's most extreme environments, inside a black hole's singularity, or at the very first moment of the Big Bang. The search for a theory that can weave these two magnificent but conflicting descriptions into a single, coherent whole has led physicists to some of the most imaginative ideas in human history. One of the most prominent is string theory. It proposes a radical shift in perspective. The fundamental building blocks of reality are not point-like particles, but unimaginably tiny, vibrating loops of energy, strings. In this view, an electron is not a dot, but a string vibrating at one specific frequency. A quark is the same type of string vibrating at a different frequency. Even the hypothetical graviton, the particle that would carry the gravitational force, emerges as a particular vibrational pattern of the string. This elegant idea naturally incorporates gravity into the quantum world, but at a cost. The mathematics of string theory only works consistently if the universe has more than the three spatial dimensions we experience, requiring extra dimensions curled up into a space too small for us to perceive. An alternative approach, loop quantum gravity, takes a different path. Instead of changing the nature of particles, it changes the nature of space itself. This theory proposes that spacetime is not a smooth, continuous backdrop. It is granular, woven from a fabric of tiny, finite loops. These loops form a network of spin foams, a dynamic, discrete structure that replaces the chaotic quantum foam. In this picture, you cannot divide space infinitely. There is a smallest possible volume, a quantum of space, just as light comes in indivisible photons. This quantization of space itself resolves the infinite densities that plague other theories at the center of black holes. Stephen Hawking long emphasized the critical need for such a theory, suggesting that general relativity and quantum theory both cannot be completely correct, as they contradict each other. He believed that finding a theory of quantum gravity would be the ultimate triumph of human reason. To visualize this unification, think of the cosmos as a vast, dynamic tapestry. The threads of this tapestry are the quantum fields for every particle and force. The loom on which they are woven is spacetime itself. A theory of quantum gravity would not only describe the threads but also the very mechanism of the loom, explaining how the woven pattern emerges from the individual stitches. This pursuit leads to a staggering possibility. Could a complete theory of quantum gravity finally allow us to peer past the veil of the Big Bang? Our current physics hits a wall at that initial singularity, a point of infinite density where all known laws fail. But if space and time are quantized, there may be no true singularity, only a quantum bridge to a previous cosmic phase, or a bounce from a contracting universe. Unifying the cosmos of the very large with the realm of the very small is not just an academic exercise. It is the essential final step to seeing the deep structure of reality as a truly interconnected and complete whole. The very fabric of spacetime may be a magnificent illusion, a cosmic sleight of hand on the grandest scale. This is the holographic principle, a theory so radical it suggests our rich, three-dimensional universe is nothing more than a projection from a two-dimensional surface. Much like the shimmering, three-dimensional image on your credit card emerges from a flat, patterned film. The genesis of this astonishing idea lies in the paradoxical physics of black holes. When matter falls into a black hole, it seems to vanish, taking its information with it. But this violates a fundamental tenet of quantum mechanics, which states that information can never be truly destroyed. Theorists like Leonard Susskind, grappling with this information paradox, made a profound discovery. They realized that all the information describing everything that falls into a black hole is not lost inside its mysterious interior. Instead, it is perfectly encoded and preserved on the black hole's two-dimensional boundary, its event horizon. The three-dimensional world is painted onto its two-dimensional surface. This holographic principle was then elevated from a black hole curiosity to a possible feature of our entire universe through a mathematical masterpiece known as the AD/CFT correspondence. This is a concept from string theory that provides a concrete, albeit theoretical, example of holography in action. It proposes a perfect duality, a complete dictionary, between a hypothetical gravity-filled universe, which has a specific type of warped geometry, and a quantum field theory that lives on its lower dimensional boundary. The mind-bending implication is that a universe with gravity, like our own, could be entirely equivalent to a quantum system without gravity that exists on its remote outer edge. To grasp this, think of the experience of watching a movie. The images you see have depth, movement, and a compelling three-dimensional reality. Yet all that information, every character, every landscape, is stored on the two-dimensional surface of the film reel or digital file. The holographic universe suggests we are not the viewers, but the characters in the movie, and our entire reality is the projection. This shatters our classical understanding of locality, the idea that objects can only be influenced by their immediate surroundings. In a holographic universe, what happens here could be fundamentally linked to processes happening on a distant, lower-dimensional surface. If this is true, then our perceived reality, with its solidity and volume, is a kind of emergent illusion. The true, fundamental workings of the cosmos may be playing out on a thin, distant shell we can never perceive. This forces a deeply reflective question. If our universe is a hologram, a magnificent projection, then what is the nature of the source code? What are the fundamental bits of information, the ones and zeros, being processed on that cosmic boundary to generate the breathtaking complexity of our world? The holographic principle points toward a reality where information itself is the ultimate, indivisible substance from which all else is woven. The universe might be built not from particles or forces, but from something far more fundamental, pure information. This is the radical proposal of physicist John Archibald Wheeler, who coined the phrase "it from bit." In this view, every particle, every force interaction, every event in the cosmos is ultimately a form of yes or no answer, a binary choice. The physical world, the it, emerges from an immaterial foundation of information bits. Quantum mechanics provides a powerful clue for this perspective. Before a particle is measured, it exists in a blurry cloud of probabilities, a superposition of all possible states. It is only when an observation is made, when a question is asked of the universe, that it responds with a definite answer, collapsing the probabilities into a single, concrete outcome. This measurement problem suggests that the act of acquiring information is not a passive reading of a pre-existing reality, but an active process that brings specific aspects of that reality into being. Wheeler himself captured this profound interdependence when he stated, "The universe does not exist out there independent of us. We are inescapably involved in bringing about that which appears to be happening." The evolution of the cosmos itself can be seen through this lens of information processing. The early universe, a hot, dense, and highly ordered state, possessed very low entropy, meaning it held a relatively small amount of information. As it expanded and cooled, the number of possible arrangements for its particles exploded, and with it, the total information content. This cosmic computation, the relentless shuffling of bits, drove the formation of ever more complex structures, from the first stars to the neural networks in our brains. A compelling, though speculative, analogy is to think of the universe as a vast, self-executing computer simulation. The underlying code, the fundamental laws of physics, are the algorithms. The particles and forces we observe are the rendered graphics, the user interface of a deeper, informational reality. This leads to a staggering question that pushes the boundaries of science and philosophy. If the universe is a giant, ongoing quantum computation, what or who is the programmer? The very act of observation seems to be a crucial part of the cosmic circuit, forcing us to consider whether consciousness itself is not merely a product of reality, but a necessary participant in its continuous creation. But where does that leave us, the observer? The quantum world presents a riddle that strikes at the very heart of reality, the measurement problem. At its core is the wave function, a mathematical description that encapsulates all the possible states of a particle, like an electron that is spinning both up and down at the same time. This state of superposition is perfectly valid until the moment it is measured. Then, the wave function collapses, and the particle assumes a single, definite property. The great mystery is what exactly constitutes a measurement. Is it the physical interaction with a detector, or does it require a conscious mind to register the result? This is the observer effect in its most profound form. The most famous interpretation, the Copenhagen interpretation championed by Niels Bohr, essentially sidesteps the issue. It posits a sharp divide between the quantum world and the classical world of our instruments, stating that the wave function collapses upon interaction with a macroscopic measuring device. It is a practical recipe for doing physics, but it offers no deeper explanation for why this transition occurs. In stark contrast, the many worlds interpretation offers a breathtaking alternative. It suggests that the wave function never collapses. Instead, at the moment of measurement, the universe splits into multiple branches. In one reality, you see the electron spinning up. In another, an identical version of you sees it spinning down. Every possible outcome of every quantum event is realized in its own separate, non-communicating universe. This interpretation elegantly removes the need for a special observer, but at the cost of an infinitely proliferating multiverse. Then there are more speculative ideas. The physicist Eugene Wigner famously proposed a thought experiment questioning what would happen if a friend performed a measurement inside an isolated lab. Wigner argued that only when he, the conscious observer outside the lab, learned the result would the wave function finally collapse. This places consciousness itself as the ultimate agent that crystallizes reality from a haze of possibilities. This leads to the ancient philosophical puzzle of the tree falling in an empty forest. Does it make a sound if no one is there to hear it? From a quantum perspective, the question becomes far more radical. Does the tree, or even the forest itself, exist in a definite state without an observer? Most physicists are deeply uncomfortable linking consciousness directly to quantum mechanics, viewing it as a slippery slope into mysticism. They point out that detectors and cameras can record definite outcomes without a human present, suggesting that any complex, irreversible interaction can cause decoherence, the process that makes quantum probabilities appear to collapse into classical certainty. Yet, the puzzle remains. The observer effect forces us to confront the fact that we are not passive witnesses to a pre-formed reality. We are active participants in a cosmic process that seems to require interaction to become concrete. So, does reality require an observer to exist? Perhaps the very structure of the cosmos, from the quantum foam to the cosmic web, is not a static edifice but a dynamic potentiality, a symphony of possibilities that only resolves into a single, shared melody through the act of observation itself. Isaac Newton once described himself as a boy playing on the seashore, finding a smoother pebble or a prettier shell than ordinary, while the great ocean of truth lay all undiscovered before him. Centuries later, we stand on a far more sophisticated shore, yet the ocean of reality stretches into a horizon of profound mysteries. Our journey through the deep structure of reality, from the quantum foam to the cosmic web, ultimately brings us face to face with the limits of our own knowledge. There are boundaries, both in scale and understanding, beyond which our current physics cannot see. At the smallest end of the spectrum lies the Planck scale, a realm so tiny that our very concepts of space and time break down. Here, the universe becomes a domain of pure potentiality where general relativity and quantum mechanics are at war, and our mathematical tools fail. It is a frontier we know must exist, but one we cannot yet explore, a shore we can see but not yet step onto. This is an epistemic limit, a fundamental boundary to what we can currently know. Our cosmic map is similarly filled with blank regions labeled with the names of our ignorance. We call them dark matter and dark energy, Yet these are just placeholders for forces and substances that make up 95% of the universe, yet remain completely invisible to our detectors. Why does the universe contain so much more matter than antimatter? A tiny but crucial asymmetry that allowed anything at all to exist instead of everything annihilating in a flash of light. And what were the true initial conditions of the Big Bang, the singular moment that set all of this in motion? These are not minor puzzles. They are gaping holes in our understanding of reality's architecture. Yet, it is precisely these gaps that drive science forward. Every blank space on the map is an invitation to explore, a call to develop new theories and build new instruments. The unknown is not a wall but a horizon. What might lie beyond our current frameworks? Perhaps dimensions curled into shapes we cannot perceive, or a multiverse of bubbling cosmic domains, each with its own unique physics. Acknowledging the vastness of the unknown is not a surrender. It is the most honest and exciting part of the journey, a reminder that the deep structure of reality still holds secrets far grander than we have yet dreamed. These instruments are our civilization's extended senses, allowing us to touch the quantum foam and gaze across the cosmic web. The Large Hadron Collider, buried deep beneath the Swiss-French border, is more than the world's most powerful microscope. It is a time machine. By smashing protons together at velocities nearing the speed of light, it recreates, for a fleeting instant, the conditions that existed a fraction of a second after the Big Bang. It was in this man-made fireball that the Higgs boson was finally captured, confirming the existence of the field that gives particles mass. Meanwhile, floating at a point 1,000,000 miles from Earth, the James Webb Space Telescope acts as humanity's ultimate eye, its golden mirrors collecting the faintest whispers of infrared light from the earliest stars and galaxies. It sees not with light, but with time itself, observing the universe as it was when its great structures were first being woven together. These are not solitary tools, they are part of a global network of discovery. The Laser Interferometer Gravitational Wave Observatory, or LIGO, uses lasers traveling down 4-kilometer-long vacuum tunnels to detect the infinitesimal ripples in spacetime caused by cataclysmic events like colliding black holes. For the first time, we are not just seeing the universe, we are listening to it, hearing the subtle vibrations of its fabric. And orbiting satellites like Planck have charted the cosmic microwave background with such exquisite precision that we can read the temperature fluctuations that seeded all future structure. These technological marvels work in concert, probing reality from the smallest scales to the largest. It is as if we have combined the most powerful microscope with the most far-seeing telescope, creating a single instrument that spans the entire spectrum of existence. Yet the pace of innovation only accelerates. Plans are already underway for even more ambitious endeavors. Future particle colliders, with circumferences 10 times larger than the Large Hadron Collider, aim to probe deeper into the mystery of dark matter and the hierarchy of forces. New space-based gravitational wave observatories will listen for the faint hum from the universe's very first moments. Alongside these physical instruments, we have built digital ones, vast supercomputer simulations that act as virtual universes. By programming the known laws of physics, scientists can watch as a smooth, hot soup of particles evolves over billions of simulated years, condensing into the familiar cosmic web of filaments and voids. These simulations allow us to test our theories on a grand scale, asking what happens if we tweak the amount of dark energy or alter the properties of dark matter. They reveal whether our understanding of the deep structure is robust or if it contains hidden flaws. This entire endeavor is a profoundly human collaboration, involving thousands of scientists, engineers, and technicians from dozens of nations, all working to decode the universe's blueprints. With every new generation of technology, we peel back another layer of reality. What profound secrets will the next wave of innovation reveal about the nature of consciousness, the origin of spacetime, or the ultimate fate of our cosmic home. Plato's ancient allegory of the cave feels startlingly modern today. Prisoners chained since birth mistake flickering shadows on a wall for the whole of reality, never suspecting the vibrant world casting those shadows just outside their view. Modern physics suggests we are in a similar bind. Our senses, and even our most advanced instruments, may only reveal a narrow slice of a much deeper and more intricate reality. The solid world we touch, the linear time we experience, these may be the shadows. The quantum foam, the cosmic web, the holographic principle, these are hints of the firelight outside the cave. This realization forces profound philosophical questions into the open. What is the true nature of existence if the vacuum of space is a seething ocean of energy? What is time if it can be warped by gravity or may not be fundamental at all? The classical universe of Isaac Newton was a predictable clockwork, where every effect had a clear cause and the future was determined by the past. Quantum mechanics shatters that determinism. At its heart, reality is probabilistic, governed by chance and potentiality until an observation crystallizes one possibility into fact. This challenges our deepest intuitions about causality. An event does not necessarily have a single, local cause. The phenomenon of quantum entanglement, what Einstein called spooky action at a distance, shows that two particles can be instantaneously connected across vast distances, as if the space between them does not exist. This non-locality suggests the universe is profoundly interconnected in ways that defy our classical understanding. The philosopher Immanuel Kant argued centuries ago that we can never know the thing in itself, the true nature of reality. We only perceive the phenomenon, the world as filtered through the structures of our own minds, through our innate concepts of space and time. Quantum mechanics and cosmology seem to affirm this. We are not passive observers reading a pre-written book. We are active participants, and the very act of reading seems to influence the story. So where does that leave our sense of self, our belief in free will? If the cosmos is a deterministic web of cause and effect from the Big Bang onward, is choice an illusion? Or does the inherent randomness at the quantum scale inject genuine novelty and freedom into the universe, allowing for a future that is not yet written? This is not merely an academic debate. It strikes at the core of what it means to be human. Consider the experience of a dream. Within the dream, the world feels solid, the events logical, your identity firm. But upon waking, you realize that reality was entirely different, a construct of your sleeping mind. Could our waking reality be a dream within a still deeper dream? A persistent illusion generated by a more fundamental layer of information or consciousness? If the deep structure of reality is a seamless, interconnected whole, then our perception of being separate individuals is another shadow on the cave wall. We are not merely in the universe is in us. The iron in our blood was forged in a long-dead star, and the quantum fields that give us substance are the same fields that ripple through the cosmic web. In a cosmos so vast and so deeply structured, what is the meaning of a single human life? The answer may not be a destination to find, but a relationship to cultivate, a continuous awakening to the magnificent and mysterious whole of which we are an inseparable part. The precise strength of gravity feels like a cosmic coincidence. If it were just a fraction stronger, the universe would have collapsed back on itself long ago. If it were slightly weaker, galaxies and stars could never have coalesced from the primordial gas. This is not the only constant that seems perfectly calibrated. The force binding atomic nuclei, the mass of an electron, the very energy of empty space, all appear balanced on a razor's edge, set to values that allow for the existence of complex chemistry and, ultimately, life itself. It is as if the universe's fundamental dials were tuned to a very specific station, and that station is us. This apparent fine-tuning leads to one of the most profound and debated ideas in cosmology, the Anthropic Principle. Coined by physicist Brandon Carter, the principle comes in two forms. The weak Anthropic Principle is a simple statement of selective observation. We should not be surprised to find ourselves in a universe capable of sustaining conscious life, because in a universe that was inhospitable, we would not be here to observe anything at all. It is a cosmic version of the survivor's bias. The strong Anthropic Principle takes a much more radical stance. It suggests that the universe must, in some sense, have properties that allow life to develop within it at some stage in its history. This version edges toward the idea of a universe with a purpose, or at least a built-in bias toward complexity and observation. A wonderful analogy, often attributed to Douglas Adams, illustrates the weak version perfectly. A puddle of water, having just filled a hole in the ground, looks around and thinks, "This is remarkable. This hole I am in fits me perfectly. Its contours match my shape exactly. It must have been designed just for me." The puddle, of course, fails to see that it is the one that has conformed to the hole, not the other way around. In the same way, perhaps we are the puddle, and our universe is the hole. We evolve to fit the specific conditions we find, not the other way around. This line of thinking finds a powerful, and some say natural, explanation in the Multiverse Hypothesis. If our cosmos is just one bubble in a vast, perhaps infinite, foam of universes, each with its own random set of physical constants and laws, then it is no surprise that we find ourselves in one of the rare, life-friendly bubbles. In most universes, the constants would be wrong, and no one would be there to notice. Our existence, then, is not a miracle of design, but a statistical inevitability in a vast enough landscape of possibilities. This forces a deeply personal and reflective question upon us. Does the universe seem finely tuned for life because of a profound, underlying teleology, a direction woven into the fabric of reality? Or are we simply the beneficiaries of an unimaginable cosmic lottery, a lucky accident in a single universe amid an infinite sea of lifeless emptiness? The Anthropic Principle ties our own existence directly to the deepest architecture of the cosmos, making the observer an integral part of the story of reality. Our single universe might be just one page in an infinite cosmic library. This is the Multiverse Hypothesis, a vision of reality that expands our cosmic horizon beyond comprehension. It suggests that what we call the universe is merely a single bubble in a vast, bubbling foam of universes, each with its own unique set of physical laws and fundamental constants. Some of these cosmic domains might have stronger gravity, making them collapse instantly. Others might have weaker nuclear forces, preventing atoms from ever forming. In this grand tapestry of possibilities, our universe is not special. It is simply one of the rare, stable configurations where galaxies, stars, and life could eventually arise. This staggering idea is not pure speculation. It emerges naturally from our most robust theories of the early cosmos. The theory of cosmic inflation proposes that our universe underwent a period of hyper-fast expansion. But if this inflationary process can happen once, what is to stop it from happening again in different places, birthing countless other bubble universes in an eternally inflating meta-universe? Similarly, string theory, with its vast landscape of possible solutions, suggests there could be 10 to the 500 different ways to compactify its extra dimensions, each corresponding to a universe with a completely different physics. The multiverse itself comes in levels. The simplest level is an infinite expanse of space, where regions so distant from us that their light has never reached us might have different arrangements of matter, essentially other Hubble volumes. A more radical level involves universes with genuinely different physical constants, born from separate inflationary bubbles or different string theory vacua. To grasp this, picture an endless forest after a rainstorm. Countless bubbles rest on the leaves. Each one is a perfect, shimmering sphere, a self-contained world reflecting the sky. Most are similar, but some are larger, some smaller, some are merging, and some are popping. Our entire cosmos could be one such bubble on a leaf in an infinite woodland. This framework offers a powerful, if humbling, explanation for the apparent fine-tuning of our universe. We do not need to invoke a designer. In a sufficiently vast multiverse, every possible combination of physical parameters will be realized somewhere. We, of course, can only find ourselves in one of the bubbles where the constants allow for our existence. The physicist Max Tegmark pushes this even further with his mathematical universe hypothesis. He proposes that every mathematical structure that can exist does exist as a physical reality. In this view, reality is not just described by mathematics, it is mathematics. We simply inhabit one particular mathematical structure that has complex enough laws to contain self-aware subsystems like us. This leads to a question that pushes the very limits of science. If the multiverse is real, could we ever hope to find tangible evidence for other universes? Some cosmologists suggest that if our bubble universe collided with another in the distant past, the imprint of that collision might be etched into the cosmic microwave background, a faint, circular bruise on the oldest light in the sky. While such a signal has been sought, it remains elusive. The search forces us to consider whether some layers of reality are forever beyond our observational reach, leaving the multiverse as a beautiful, untestable possibility. The universe is not a timeless monument, but a story still being written, and every story has an ending. That final chapter is dictated by the relentless push of dark energy, which is stretching the cosmic web ever thinner. One possible future, the Big Freeze, is a slow, cold fade into oblivion. Over trillions of years, as galaxies continue to recede from one another, the last stars will exhaust their fuel and wink out. The cosmos will become a dark graveyard populated only by the fading embers of stellar remnants, neutron stars, and black holes. Even these will not last forever. Through a process theorized by Stephen Hawking, black holes themselves will slowly evaporate, radiating away their mass over unimaginable eons until they too vanish in a final puff of particles. The universe will approach a state of maximum entropy, a featureless sea of near absolute zero temperature where energy is so evenly distributed that no work can be done, and no new structure can ever form. This is the heat death, the ultimate equilibrium where the cosmic clock simply runs down. But dark energy holds a more violent alternative. If its repulsive force strengthens over time, it could lead to a big rip. In this scenario, the accelerating expansion would not just separate galaxies. It would become so powerful that it would overcome all the forces holding things together. First, galaxy clusters would be torn apart. Then, individual galaxies. As the end neared, stars would be ripped from their solar systems and planets would be shredded. In the final moments, even atoms and atomic nuclei would be torn asunder, the very fabric of spacetime itself rupturing in a catastrophic finale. The fate of everything hinges on the precise nature of dark energy, a force we are only beginning to comprehend. This cosmic evolution unfolds on a timeline that dwarfs human history. We live in the stelliferous era, the age of stars, a brilliant but brief period in the universe's long life. In the far future, after the last star dies, the universe will enter the degenerate era, dominated by those cooling stellar remnants. This will be followed by the black hole era, where only these gravitational giants remain, slowly evaporating. The final act is the dark era, an eternal, silent epoch of near nothingness. To visualize this, think of a magnificent firework display. The Big Bang is the initial, spectacular explosion. The formation of stars and galaxies are the brilliant, colorful sparks filling the sky. But now the display is past its peak. The sparks are drifting apart, growing dimmer and colder, destined to fade into a vast and permanent darkness. Are these the only possibilities? Some theories suggest a more cyclical universe, where a big crunch follows the expansion, leading to a new Big Bang in an endless cycle of cosmic death and rebirth. Another speculative idea is vacuum decay, where a bubble of a more stable, true vacuum forms somewhere in space and expands at the speed of light, rewriting the fundamental laws of physics as it goes and effectively erasing the universe as we know it. These are not prophecies, but extrapolations of the physical laws we are desperately trying to understand, contemplating a future where every structure dissolves and every light goes out. What legacy could our universe possibly leave behind in that infinite, silent darkness? That faint echo from the Big Bang and the frantic dance of a quantum field are not separate stories. They are different verses of the same cosmic poem. We have journeyed through the layers, from the seething quantum foam to the vast cosmic web, and a stunning truth emerges. Reality is not a set of stacked boxes, one resting neatly upon the other. It is a single, unified system, a grand tapestry where threads from the smallest scale weave directly into the largest structures. The ghostly tug of a dark matter particle, a relic from the first second, dictates the path of a galaxy a billion light-years wide. The same quantum uncertainty that governs an electron's blurry position was stretched by cosmic inflation into the gravitational seeds for entire superclusters. Our understanding of the very small, forged in particle colliders, illuminates the story of the very large, written across the night sky. This deep structure is not a linear hierarchy but a vibrant network of relationships, where each layer both influences and emerges from the others. It is like a magnificent symphony. You have the high, delicate strings of quantum fluctuations, the deep, resonant brass of galactic clusters, the rhythmic percussion of stellar fusion, and the haunting, pervasive melody of dark energy. Alone, each section has its own character and rules, but together they create a harmonious whole, a single piece of music that is our universe. Albert Einstein once expressed a sense of wonder at this very fact, stating that the most incomprehensible thing about the universe is that it is comprehensible. That we, with our limited senses and brief lives, can uncover these profound connections is a testament to the power of human curiosity. So how do we, as humans, begin to truly grasp this unity? We stand at the nexus, a point where the quantum and the cosmic meet, and we find that we are not merely observers of this tapestry, but are woven from its very threads. From the frenetic quantum foam to the majestic cosmic web, we have traced the hidden architecture of existence itself. This journey reveals a universe not of separate layers, but of a deeply unified whole, where the smallest fluctuations birth the largest structures. We have seen how empty space is a vibrant sea of energy, how fleeting virtual particles give rise to stable matter, and how the dance of quantum fields builds everything from a single atom to a swirling galaxy. The invisible hands of dark matter and dark energy sculpt this grand design, pulling galaxies together while pushing the cosmos apart. These discoveries do not just answer questions, they open profound new mysteries about our own place in this vast tapestry. We are made of stardust, yes, but we are also the universe become conscious, a means for the cosmos to look back upon itself and wonder. Carl Sagan's timeless words ring true: we are a way for the cosmos to know itself. This knowledge is not a cold collection of facts, but an invitation to live with a deepened sense of awe. Let it color your perception of the world, from the solidity of the ground beneath your feet to the vastness of the night sky. The quest to understand reality is humanity's greatest adventure, and it is far from over. Each answer peels back a layer to reveal a new and more beautiful question. I encourage you to carry this curiosity forward, to question everything, and to share your own wonders in the comments below. Thank you for joining this exploration of the deep structure of reality. If these journeys into the cosmos inspire you, subscribe for more, and let us continue this adventure